Deep within the constellation Taurus, approximately 6,500 light-years from Earth, lies the magnificent Crab Nebula, a primary entry in the Messier catalogue, a list of celestial objects that astronomers still use today. First observed in the mid-18th century, it didn't take astronomers long to associate this cloud of interstellar gas with a great supernova explosion that illuminated the sky in that same region around 700 years prior. Since then, the Crab Nebula has remained a source of intrigue, becoming one of the most well-known and extensively studied objects in the sky. As observational technology advanced, the nebula continued to reveal surprises. By the late 1960s, radio astronomy uncovered an extraordinary find within the Crab Nebula, a small but extreme remnant of the supernova, a rapidly rotating neutron star. Neutron stars, the final stage of matter before it can transform into a black hole, play a crucial role in seeding our galaxy with essential ingredients for life. In this exploration, we delve into these mind-bending objects, with a focus on the intense power of pulsars. Neutron stars are not remnants of Sun-like stars. When a Sun-like star nears the end of its life cycle, it expands into a red giant and ultimately sheds its outer layers, exposing its core, which then compacts into a white dwarf. However, for much larger stars, at least 10 times the mass of our Sun, a different fate awaits. Rather than dissipating, these massive stars eventually exhaust their fuel and collapse under their immense weight, compressing their iron cores until they explosively rebound in a supernova. The outcome after such a collapse depends on the mass of the star's core. If it exceeds roughly 3 times the mass of our Sun, gravitational forces override all resistance, compressing matter beyond the Schwarzschild radius and forming a black hole. But if the core mass falls below this critical threshold, the collapsing core encounters a final resistance. As molecules are compressed, temperatures soar to such levels that atomic structures break down, converting the core's iron into a dense soup of subatomic particles. Free electrons merge with protons to create an abundance of neutral neutrons. This dense core, now reduced to a fraction of its original size and brimming with neutrons, begins to resist further gravitational collapse due to degeneracy pressure. Since neutrons cannot occupy the same quantum state in close quarters, they shift states in response to nearby neutrons, creating a force that counters compression. Supported by nuclear forces within atoms, this pressure halts the collapse, resulting in a neutron star, about 25 kilometers wide and as dense as an atomic nucleus. The star's outer layers explode in a supernova, leaving behind this compact neutron star, the last stage before potentially becoming a black hole. A neutron star typically has a mass up to 2 times that of our Sun compressed into a sphere no larger than a city. This compression powers some of the most extreme phenomena observed in space. Neutron stars have an outer shell of superheated iron with gravity so intense that the escape velocity exceeds half the speed of light, stretching and dilating time, as in black holes. This iron shell sizzles at millions of degrees Kelvin for hundreds of millions of years. The crust is underlaid by a crystalline mantle of a nuclear pasta, long chains of neutron-rich matter before reaching the superfluid neutronium at the core. The swirling of this superfluid, along with the star's rotation, generates an intense magnetic field, often hundreds of billions of times stronger than Earth's. These neutron stars, the universe's most powerful magnets, exhibit various electromagnetic phenomena. Although rarely seen in visible light, they appear prominently in radio, X-ray, or gamma-ray frequencies. As they spin, charged particles in the magnetosphere are accelerated towards polar caps and are ejected at relativistic speeds, emitting synchrotron radiation. Because these polar caps don't align with the rotation, they swing beams of radio energy around like a lighthouse, producing periodic radio signals observable on Earth. This pulsing radio signal led to the discovery of neutron stars in the late 1960s. The first detection was made by Jocelyn Bell Burnell, who in 1967 identified a sequence of radio pulses separated by precisely 1.3 seconds. Initially perplexing scientists, the signals were ultimately attributed to naturally occurring neutron stars. Since then, over 3,200 neutron stars, most of which are radio pulsars, have been catalogued. The estimated number of neutron stars in the Milky Way alone could be up to 1 billion, though most are now cold and slowed down, rendering them undetectable. A pulsar in isolation gradually loses momentum, a process known as spinning down, due to the radiation of gravitational and electromagnetic energy. However, if a pulsar has a companion star, it may spin up as it accretes matter, emitting X-rays as particles decelerate within the magnetosphere. If the companion is a small star, it forms a low-mass X-ray binary, a larger star creates a high-mass binary. This process can lead to incredibly rapid spin rates of hundreds of revolutions per second. Pulsars that spin faster than 100 times per second are known as millisecond pulsars or recycled pulsars, producing highly regular signals sensitive to minute gravitational shifts. In 1992, 2 exoplanets were discovered around the millisecond pulsar B1257-12. With masses and diameters comparable to our Moon, they remain the smallest known extrasolar bodies. The fastest pulsar, J1748-2446 AD, spins at 716 Hz or 43,000 revolutions per minute, although rotation isn't the main determinant of magnetic field strength. Factors like the progenitor star's magnetic strength, such as in the case of massive magnetic helium stars, play a greater role. These extremely magnetized stars, known as magnetars, were first identified in 1979 with gamma-ray bursts. A notable flare in 2004 from magnetar 1806-20 emitted energy equivalent to 150,000 years of solar output, causing a change in Earth's atmospheric ionization despite being 40,000 light-years away. Such an outburst within 10 light-years could strip Earth's atmosphere, boiling away oceans and making the planet uninhabitable. Starquakes on magnetars also generate radio bursts, which may share origins with fast radio bursts, observed in the sky without a definitive explanation. The discovery of binary pulsars by Joseph Taylor and Russell Hulse in 1993 provided observational proof for general relativity, with the pulsars' orbits decaying as they emitted gravitational waves. This phenomenon would be directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. When neutron stars collide, they merge at near-light speeds, producing gravitational waves and leading to a kilonova, an explosion enriched with heavy elements like gold and uranium. Kilonovae are now believed to be key sources of heavy elements in the universe, surpassing supernovae in their contribution. As colliding neutron stars merge, if the combined mass is sufficient, they may form a black hole, otherwise, they may coalesce into a heavier pulsar or a magnetar. An intermediate mass, dense enough to unbind neutrons but not form an event horizon, could create a boundary object, a star so dense that even neutrons break down into quarks, the fundamental particles that formed in the early universe.